IC was the so in during due to the revolution, transistors, this integrated circuit revolution was triggered. Okay, so actually, if you have any doubts regarding the background of the like fundamentals of the, if you do not have the clear aspects of the like basics of the electronic like physics, you can ask me the question, because these questions are like there is nothing to write about. Okay, so I am also confused what should I write in these things. So in the upcoming questions I might solve the questions completely. So in the next question, it is written that the question is the splitting of the discrete energy states into the continuum of energy states upon reducing the interatomic distance between the isolated atoms of the same kind is a direct consequence of. So okay, there is a splitting of the energy levels, right? Hello, you guys can listen to me, right?
Yes, yes, you're audible, loud and
Yes.
clear.
Okay,
Yes,
so
sir.
so actually what happens is, so if this is a single atom which is isolated, okay, there will be electrons and electronic levels. Okay, these are the levels of the energy levels around the atom. Okay, so around, if this is isolated, the energy levels are discrete energy levels. Okay, so as soon as, if there is another isolated atom which is very far away from their this atom, they do not have any interaction in between them. But as soon as they start interacting with each other, when they come closer from here to here, they come closer and closer, so these energy levels will start interacting with each other. Okay, so in this question, what they have asked is, what is the direct consequence of the splitting of the energy levels as they come closer, these atoms come closer. So so uh, have you studied that thing in the 12th standard, that no two electrons can occupy the same no two electrons with the same quantum number can occupy the same energy level? You must have studied this thing, right? So in that case, the so one electron can occupy this energy level. What about the other electron which is in the same state when they were isolated? So these must split into the energies in two energy levels. When two atoms come closer, the two energy states will be split. This single energy state will be split into two. When 3 will come, it will split into 3. 4 come, it will split into 4. Okay, so it will split into 3, 4, 5, 6 if there will be the n number of atoms. So n number of atoms which their energy levels are if their energy levels are interacting, so this will split into a band into n energy levels. But the energy levels, as uh, the gap between these two energy levels will decrease as more and more number of atoms come closer. Okay, so here because of this, in the field of nanotechnology opens up, because as if have you heard about the nanoparticles, right? So can you have seen the gold with the yellow color? Definitely. Can you imagine the gold can be red, green, yellow, red, green, blue? Can you think of this thing? This is because of the if that nanoparticle itself is of 2 nanometer only, 3 nanometer only. So there will be very less number of electrons, very less number of atoms in a single particle, single nanoparticle. There will be very less number of atoms. So like just imagine there are just 10 atoms in a nanoparticle. So what will happen is, so the energy difference between these, they will split into 10 energy levels. Okay, so there will be a transition, as a transition of the electron from this level to this level. So if there is a transition of electron, so it will come back, so it will emit energy, right? So it will emit energy, and th- that is what we see, the color of the color of anything. Okay, so in a solution form, you must have encountered. You just Google it. So gold nanoparticles can be of different colors other than yellow. So this is because of this thing. So in this one, actually this was the a background that I have explained too much. So it didn't require that much, but so why? So this is direct consequence of actually the Pauli's exclusion principle. As two electrons with the same quantum number cannot with have the same energy level. Okay, this is the direct consequence of the Pauli's exclusion principle. So these things you can see. So and okay, this was the second question, right? In the third question, what we can see is okay. Are there any other people who want to join? Let me check once if there are any other people. No, 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 no. Okay. So okay. So in okay, second question is, which among the following is an indirect band gap? So do you understand what is direct band gap and indirect band gap semiconductors? So if so actually I will explain what is the direct band gap and indirect band gap semiconductors are. So do you know the EK diagram? Okay, I will tell EK diagram. Okay, so in EK diagram, what happens is this is the diagram with energy versus momentum diagram, we can say. So in EK, the EK diagram is okay. This is K. In this is a reciprocal space diagram, we can say, the energy versus K diagram, energy versus momentum diagram. In this one, what happens is there is a like okay. Uh, directly I can tell this thing is this is the like parabolic relation between the energy and momentum. Okay, so this is E is equal to h square h bar square k square by 2m. So energy is directly related with the square of the momentum. So this is the parabolic relation within the free space. Okay, this electron, this is the energy of the electron when moving in a free space. So it is a parabolic kind of relation. Okay, so this is not a real space. Okay, so whenever if someone says electron is here, it that means the energy of that the momentum of that electron is zero. Okay, this is E and K, this is 0 point, and here we increase the momentum. If someone says this electron is here, that doesn't mean the electron is in the real space, it is going up or this thing. No, it is in the real space, it has the momentum which is corresponding to this one. P is equal to actually okay, just a minute. Hmm. Hmm. Okay, E is equal to h square k square by 2m, and this P is equal to h bar k. Huh. Oh yeah, okay. Well, E is equal to P by 2m, na? P square by 2m. Okay. Actually, I am writing on the screen, so it might be difficult. Actually, you can just ask the question directly. I will try to do it better as better as possible. Okay, so okay, let me check the question again. So direct and indirect band gap. So in the EK diagram, this at any particular point, in the real space, that is like this is our material. So at this point, it is they at this point. So there is a electron. Okay, so it is surrounded by atoms, surrounded by like, if it is crystalline, so there will be periodic atoms, in a period. So that is like the distance between the two atoms will be constant. So that can be in hexagonal or cubic, whatever it is. So that depends on the direction, actually. So the distance between the two atoms. So what happens is, if this electron is moving in this space, so at this particular point, it will have EK diagram at this particular point. This EK diagram also depends on the three dimensional. If this electron will go towards left, right, top, bottom, in any direction, so there will be a 3D EK diagram. So that can be anything. Okay. So, and for electron, it will be the conduction band. This is the conduction band. And for okay, for holes, which are the like vacancy of the electrons, for holes there will be something below that. So what is the lowest point of this Venn diagram, of this EK diagram? What is the lowest point? This is taken as the edge of the conduction band, and the uppermost point of this valency EK diagram of this one. So it is taken as the uh, edge of the valency band. So whatever is the difference between them is the EG. That is the band gap, actually. Okay. So if this maxima of the conduction band and the maxima of the valency band and minima of the conduction band are for the same value of K. This is the K and this is the E for this is diagram. Okay. 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 I will make the another one. So okay, this is E. This is K. Okay. So there can be any type of the like the curvature of this band. This conduction band can be of any type. And here is the curvature of the valency band. This is in the three-dimensional at a particular point. Okay. At every particular point there will be a this thing, conduction band, this EK diagram for the of EK diagram. So okay, the minima of this conduction band lies here, and maxima of this valency band is here. So whatever the distance between them, whatever the energy gap between them is the EG. Okay, this is the energy uh, band gap of the semiconductor. If this lies for the same in here, the K is like K2, and here the K is K1. So K1 and K2, this maxima and minima lies at the different values of the momentum. So therefore, this is the indirect band gap semiconductor. So for electrons, electron at this particular level to transit to go to the conduction band, so conduction band, so it will go here, so there will be a change in the K. So that is, there will be a change in momentum. It requires change in momentum. So this is a very highly inefficient process. So we call it phonon assisted kind of transition. Okay, so if, and another case is if this conduction band minima and valency band maxima both lie for the same value of k. This is k, this is e, for the same value of k. So this is the direct band gap, and this these are very these direct band gap semiconductors are very good for the applications of LEDs, solar cells, etc. LEDs maybe mainly, because in LEDs what we need is the emission of the light. So whenever there is a direct band gap, so this the electron in this conduction band will go directly to the valency band minima, valency band maxima without change in the momentum. Okay, so this is highly efficient, and these so by doing so it will release a photon corresponding to energy gap. This easy. So hc by lambda, which is hc by lambda. So this lambda will be defined by the band gap of the semiconductor. Okay, so in indirect band gap semiconductors like silicon, so there you cannot see the emission. You cannot see any LEDs which are fabricated using silicon, because we cannot, because there is no emission in the indirect band gap semiconductors. Okay, so this is the thing. So if the transition, if the conduction band minima and valency band maxima are at different values of k, so that is the indirect band gap semiconductor. If they lie at for the same value of k, so then it is the direct band gap semiconductor. Okay, so in this question what they have asked is so which of them is indirect band gap? So definitely silicon is indirect band gap semiconductor. Okay, indium arsenide, gallium arsenide, gallium nitride, all these are used for the LEDs. So whatever you have the phone, telephone, mobile phones other than OLEDs, so they were used, they were in their screens there are LEDs made of gallium arsenide, indium arsenide, and gallium nitride. Okay. So gallium nitride, I think this is very high band gap semiconductor. So blue LEDs are, I think, fabricated with gallium nitride. So that I need to check also. And another thing is next question, fourth question I am going to cover. So a key property of the semiconductor that distinguishes it from metals and insulators. Okay, in this one they have given the options. The abundance of the semiconductor material on Earth, definitely not, because there are many. Okay, silicon is a highly silicon is actually used for the semiconductor purposes only. And the ease of device manufacturing, no.
Hello.
Yes, yes.
Sorry sir for the interruption. Sorry sir for interruption. So at the end I am getting confused for question number 3. So the answer is silicon or gallium arsenide?
No. Silicon only. Silicon is the indirect band gap semiconductor.
Okay, sir. Okay.
Because silicon, okay, I will tell it again. So silicon, this, okay, it is kind of like this. This is the like K, okay, and this is the maxima. Okay, this is the valency band. This is the conduction band. Okay, so in the conduction band, so the minima of the conduction band is for different value of k. Okay, this is k. Okay, k is the momentum. Okay, so this is for the different, this is k1 and this is k is equal to 0. So the minima of the conduction band and maxima of the valency band lies at the different values of k. Okay, so whenever we take the band gap, that is a difference between the minima of the conduction band wherever it lies in the EK diagram. But this is the difference between the minima and maxima of this conduction band and valence band respectively. Okay, so this is 1.12 electron volts. Okay.
Yes, sir.
So in the next question, so the ability to tune the conductivity of the material, yeah, this is the answer. The ability to tune the conductivity of the material is that opens up the applications of the semiconductors. Actually, we can use this as in many electronic gadgets and many electronic devices because of this property of tune the conductivity of the material. So how can we do that is okay. So this is the band diagram I am making. This is the band diagram. So this is the conduction band. This is the valency band, and this is the conduction band. So okay, the basic thing in the semiconductor is this. There is a band gap. Okay, and because of this band gap, the band gap can maybe from 0.2 electron volts to several electron volts, like 3 to 4 electron volts. So that can be counted till 3 to 3.5. That we can count as a semiconductor device. Okay, because there are so with the application of the electric field, with the application of the light, we can increase the number of charge carriers in the conduction band. Okay, in the charge carriers, I am assuming in the conduction band we always see the electrons, and in the valence band we see the holes, holes. Okay, so in semiconductor, what happens is so because of the band gap, so as we shine the light, the electrons can go from valency band to the conduction band, and that energy of the light should be greater than or equal to the band gap energy. Okay, so because of this you can make photo detector, you can make LEDs, you can make solar cells. Okay, because of this phenomena only, okay, this because of this conduction band, and also with the doping, or this is the because of the band gap only, and another thing is doping. So if this is the conduction band, this is the valence band, there are very few electrons, like 10 raised in silicon. Just I'm telling about the silicon, 10 raised to power 10, around 10 raised to power 10 particles per centimeter cube, number of electrons per centimeter cube. Okay, so this is very less as compared to 10 raised to power 23 in per centimeter cube. That is the Avogadro's number, which is like 10 raised to power 23 atoms per centimeter cube. Okay, so if this 10 raised to power 10 is very less actually. Okay, so the conductivity is not that good, but we can tune the conductivity by doping, by p type or n type doping. Okay, so if we dope it with the 13th group or third group elements, okay, like boron, okay, yeah, this is, they will create an energy level here, because this boron has a, okay, someone wants to join the meeting, just a minute. Anyone else? Okay, so if boron will dope this material like silicon, p type p-type doping is because of the boron and another materials which are in the 13th group, and with the other materials like phosphorus and other. So we generally do the doping with the boron and phosphorus. Okay, they will make it n-type material. So we can actually tune the conductivity of semiconductor because of the doping. So that's why they are like realize the electronic devices because of this thing. Okay, so another thing what I was telling in the previous slide was okay this okay I don't know what to tell about what more okay. So do you have any doubts with this thing? So we can tune the conductivity with the doping, and another thing actually I wanted to tell is uh, so do you know about the FETs, field effect transistors? Anyone? You can turn on your mic because I cannot see your screen.
Yes, it is field effect
Okay,
transistor.
you know, right? Most of you might be knowing of. For those who don't know, I will just tell about the brief about the FETs. So how this is why transistors are revolutionizing, have revolutionized the world. Because initially I just can't tell you about directly that was the first question. They have revolutionized the world, but how? So this is the I think right time I can tell you about. So okay, so uh, I will tell you about the organic field effect transistors. Okay, so what we actually generally do in my this is my research work also. So I can tell you about this thing. So this is the silicon. Whatever substrate you want to take, just I am showing a single electronic device how that does that works. Okay, this is the silicon, and silicon may be highly doped. Highly doped silicon is the conducting. Okay, silicon n plus plus or p plus plus dope. Silicon plus plus is uh, the signature for the highly doped. Plus is a lesser doping, plus plus is a higher doping. That means this can work, this can be used in replacement of the metal. Okay, so there are several structures for the FET, so I will be telling you about just a single structure. So above it we can grow SiO2. Why SiO2 is because the interface for silicon dioxide interface is the best interface. Because of that only your all your electronic devices are based on this silicon dioxide interface, because this is the best interface. There are very less traps. That's why this has revolutionized the world. This silicon is the world. 95% of your electronic gadgets are based on this technology only, silicon. And in every device, whatever you can think of, whatever in electronic gadgets you can think of, have the transistor. Have the transistor. Your mobile phone, laptop, whatever this stylus, everywhere everywhere there are transistors. Okay, so okay, this is silicon dioxide. So about that there is a material that is coated, like if I am just telling you about the organic field effect transistor. So this is the material, whatever p-type material or p okay p-type, okay, p-type material. So over that there are source and drain. Okay, so what we are, this is the gate electrode. Silicon, as I told you, silicon can act as a metal, so we can connect gate here. So this is source, this is drain. What we just want to control the flow of the current through source and through drain. Okay, how can we control that? If this is the p-type semiconductor, so if I apply a positive voltage, just let's say positive voltage, what will happen is there will be accumulation of the holes at this point. No, accumulation of this is p-type. There were holes all over this material. They will because of this positive, they will be thrown out. Because of this electric field that I have applied at the gate, so there won't be any kind of channel that can conduct electricity in between source and drain. Okay, as soon as apply a negative voltage, what will happen is, so this was our channel. Okay, what will happen is the holes will accumulate at the interface in between the SiO2 and p-type material. Actually there are other pens also. There are, so holes will accumulate at this interface as soon as I apply a negative voltage. So what will happen is there will be a flow of holes in between these source and drain. As I apply, there is a positive, or as I apply a battery or whatever. Okay, and here is my resistors or bulb. Okay, so what will happen? So this can act as a switch. Okay, this can act as a switch. Whatever in your laptop or mobile phone, there are small micro LEDs. So what is controlling them? Behind them there is a FET panel. Okay, these are the devices that is in what we say in nanometer regime. That is like now currently there is 4 nanometer technology. 4 nanometer. Can you think of how small a transistor can be? 4 nanometer. 4 nanometer in the sense, this source and drain, in the distance between the source and drain can be 4 nanometer, or the smallest feature size. The smallest feature size can be anything. That can be source size also, drain size also, or the distance between the source and drain. This is the distance between the source and drain is actually the channel length. Okay, so that will come across in the subsequent lectures. I think the professor will teach about when he will teach about the this FET devices. Okay, so this can act as a source. This can act as a switch in the TFT panel. In the in your screen. So you can just think about, this is an LED, and this is connected with your battery. So, and here how you are controlling the LED? How can this brightness of the LED? How the brightness of LED can be controlled by the amount of flowing, the current flowing through the transistor, and this amount of current flowing through the transistor can be controlled the bias that we apply at the gate. Okay, so the brightness, your screen brightness, your you can see the pictures, moving pictures. How can you think the pictures are so fast moving? So what happens at that point is, so we are giving the pulses at the gate. Okay, at the gate. So that the pulses at the gate will that is kind of the refresh rate that you see, 120 hertz, whatever that comes, 60 hertz, 100 hertz. So there are screens with the like different refresh rates. Okay, so better is the refresh rate, better is the picture quality of your screen. Okay, so this was just in additive. I just wanted to tell. Okay, so because of the like tuning in the conductivity, we can do some such sort of things. Okay, because of the semiconductor only. Semiconductor has revolutionized the world, literally. So next question is the 5th question. So if anyone has the doubt in this one, you can ask me. Okay, so this was the 4th one, and 5th question I will just check. So which of the following statement describes the essence of Moore's law? So okay, this is the number of wires per unit area in the microchip doubles every. So no. So wires can be okay. So these transistors that I told you about now. So the source. Okay, okay. Say this is the like gate terminal. So and this is the another gate terminal. So if we are increasing number of transistors, so there the number of wires will also the interconnects that we can say they will also increase, but this is not because of the move. This is doesn't tell Moore's law doesn't tell about this one. And the number of transistors per unit area in a microchip gets halved. No. So this is saying half your number of transistors will get halved. So that means the chip area will get doubled. No, that cannot happen. Otherwise, so whatever we are in the current regime, that will this laptop size is like this. This laptop size will get double. That's it. This is the thing that they are saying. So that cannot happen. So and the number of transistors per unit area of in the microchip doubles. Yes. So this was the size of the chip. Okay. So initially there were some transistors in this one. So the size of the transistor, they can only 6 transistors could fit. So now the technology comes. So this now we can fit more number of transistors. Okay, so we can, instead of 6 now we can fit 12 transistors. So this is because of the improvement in the like transistor size, that improvement in the materials and lithography techniques. So this is because of that only. Lithography. You guys know about the lithography? Anyone? Lithography. Have you learned about this thing? So whatever you can think of, whatever device is, you cannot imagine without lithography. Lithography is the basic thing that is required to do to make the devices. So that 4 nanometer technology, how you get this thing, or whatever. This is because of the lithography only. How can you make such a smaller devices, and why cannot we this thing cannot be achieved previously, like 2 micron, or the devices were of higher sizes, because of the improvement in the lithography technique only because of that only we have reached to the point of this 4 nanometer technology. So lithography is the key, and also this that have a that because of that only we can realize the miniaturization of the devices. With this miniaturization of devices is because of the lithography only. Okay, so this is the like isme C in this one. C is the answer. The number of transistor per unit area in a microchip gets doubled. Okay, so this is because of the pure lithography only. Okay. I will just check once. Admit. Anyone else is there? Hmm. Okay. So now another question is the relation between energy and wave vector is the in the reciprocal space. For free electron is blank, and the okay, that is I have already covered this one. Okay, I have already covered, but uh, there is concept of another effective mass also. So in the next one, I will do that also. So in the free space, that as I told you about this, E is equal to h square k square by 2m. Okay. So this is the parabolic relation that it is. talking about that I already covered in, okay, in the wave vector. Okay, the relation between the wave vector, this k is nothing but the wave vector, or this is directly related to the momentum of the electron. Okay, momentum of electron or hole or any particle, whatever you can say. Mhm. For free electrons, so is this relation holds only for the free electrons. Okay, free electrons, or this is asking, or free holes also, you can say free holes or electrons, they are asking how the free electrons only. So this relation is holding for the free electrons, and this is like parabolic relation. This is E and this is K. Okay, this is EK diagram. So this is for the free space, but what happens when the electron move in a lattice? Okay, so in a like material, how that electron moves. So for crystalline, there this is a crystalline material that is I am showing you. Okay, this is material uh, with like atoms within equal space in between that. Okay, so we can model the potential, because potential of the periodic, we say it a periodic potential, because the atoms are at the equidistance and they forms a period of the atoms. Because of that only we say a periodic potential, and they create a potential well because of that. And this this can be modeled into the equations. Okay, this can be, and uh, this uh, there is an equation uh, which relates the Schrodinger wave equation. Okay, Schrodinger Schrodinger wave equation. So this was modeled with the Croning-Penny model also, which they have solved this Schrodinger wave equation with the Croning-Penny model, and they came with, okay, this okay, yeah, they uh, so in by solving it, okay, okay, by solving the this Schrodinger wave equation for the periodic potential, we can get another equation. So we can solve it for a periodic potential. Just say that electron is moving in a periodic potential. So what we get from that, the equation is, so this EK diagram, this EK diagram is a bit distorted in the energy. This is energy and this is K. So what happens is, this was the EK diagram. So what happened with that is, so when the electron moves in a in a space with other atoms, so why it feels the potential of the other atoms also. So it is not free, but it is bounded. It is deflected. There are so many things happen when an electron moves inside a lattice. Okay, it like scatters and all these things happens, that so they are accounted in this Schrodinger wave equation. And what they so actually what happens is, so they have this EK diagram becomes a distorted diagram. Okay, so it is like this, and there is a gap in the energy, but there is no gap in the momentum. There is no gap in the momentum, but there is gap in the energy. So it will start from the same point where it left off. Okay, here, but there, in terms of energy, there is a gap. this E, there is a gap. So for all the energies there is no K. For these energies there is no K, but for all the values of K, whatever it is, there is some energy defined. But for not for all the energies, for these energies there is no K. There is no K. Okay. But so this is a bit distorted. So what we call in electronics, this is the, I am not a like physicist, but I have studied the electronics. So this is the first brilliant zone. So you people from maybe from the this physics background, you might be knowing all about this. I just know a little bit about this. This is the first brilliant zone. Okay. uh, so okay, let me check the question again. What they are asking, I just forgot that. Hmm. For effective mass also they are asking. Okay, so also the relationship between the E and K is equal to E is equal to h square k square by 2 2 m star. Now this is the star. This is m star, because this now when this electron is moving through the lattice, so this is not the real mass, whatever this is, whatever the mass of the electron, but not the this mass, the real mass. The mass changes as it moves in the lattice. So as it moves in the lattice, the mass changes. So for, and it also depends on material to material. Every material will have the different effective mass. So this is the effective mass, and this effective mass captures the curvature of the ek diagram. Okay, curvature of the effective mass of electron captures the curvature of the conduction band, and effective mass of hole, mh star we call it, or me star for electron we call it. They captures this captures the curvature of curvature of this valency band. Okay, valency band of the ek diagram. Oh, okay, valency we cannot call it band, because band is different thing. Valency diagram, valency whatever. Okay, and me captures the curvature of the ek diagram for the conduction band. Okay, so this is the thing. So and also what we can see is there is m star d2e by dk square. huh m just a minute. M star is equal to 1 in h cross square over d2e by dk square. Okay, this is the relation between the effective mass and the curvature of the ek diagram. Okay, so what happens is, okay, if this is known, we call it curvature. Okay, in the next slide. Okay, d2e by dk square is curvature. Okay, curvature. If the and effective mass m star is inversely proportional to the curvature. Okay, so is it is if curvature is higher, m star is lower. Okay, m star is lower, m star effective mass is lower. If the effective mass is lower, then there comes another things also, that mobility, conductivity, and all these things will come. So mobility will be higher. Okay, I can show you the relation with m star increases, mobility mu decreases. Okay, m star, sorry for my writing skills, I'm really very bad at this. So m star decreases, mu increases. Okay, so uh, this is the relationship between the mobility and the effective mass. So if the curvature increases, we can directly say if the curvature increases, mobility of the hole or electron in the conduction band or valency band will be lower. Okay, curvature increases, will be higher. Uh, I'm really okay. Uh, so in this one, so potential and the moment of the electron in the periodic potential is dependent of the effective mass. So this was the case. So parabolic, we have already seen E is equal to h bar square k square by 2m. That was the parabolic relation, and from that parabolic relation we have uh, established a relationship between the effective mass and the curvature of the uh, uh, band, ek diagram. Okay, yeah. So now the seventh question comes. So the curvature of the conduction band in the ek diagram of material A is more than material B. The effective mass of the and the mobility of the material B as compared to A is respectively. Okay, okay. Now just only now we have done the okay. Okay, they are directly saying the curvature, right? Okay, ek diagram A is more. Okay, the okay curvature. Okay, m star is inversely proportional to curvature. Okay, so what they are saying is just uh, what they are saying is the curvature of conduction band in ek diagram of material A is more. A का curvature ज़्यादा है. Okay, so what will happen is then B, the effective mass will be okay, curvature more, effective mass will be lesser. M star will be lesser. If B, effective mass less, m star will be higher. Okay, so this is the thing, effective mass and mobility of the material B as compared to A. Huh. So effective mass of B will be higher. Okay, that is they asking, will be higher, and mobility is directly okay, directly proportional to the mobility. Okay, yeah, okay, just A curvature is higher, m star is lower, mobility is higher, and mu will be higher because of low effective mass, and mobility will be lesser in this case. So in B, in material B, what will happen is uh, effective mass is higher and mobility is lower. Okay, so A option will be correct in this one. So okay, I think you might have confused in this one. Anyone has a confusion in this one? Hello, you can ask a question in this particular question.
Hello,
Rohit?
sir. I have sir one question.
Yes, 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 yes.
Sir, any material for calculating effective mass that will be calculating practically or EK diagram. How can I derive this EK diagram for any material?
For any material, you cannot, because you need to solve for that. You need to solve a Schrodinger equation. Okay,
Okay, sir.
and solving you can. There are like uh, supercomputers. They can solve that because we whatever we have read about is the hydrogen-like atom. Okay, in Schrodinger wave equation we have a potential well, a single atom, but in a material there is interaction with n number of other atoms. So considering these much number of atoms in a Schrodinger wave equation, it is painful. never. You can never calculate that thing. But what we do practically, we can calculate the mobility directly. We can calculate the mobility directly, but with the other relations we can calculate the effective mass. Okay, with the back calculations. Do you know about the about hall measurements? Hall measurements, right?
No, sir, no idea, sir.
Okay, no idea. I think professor will teach that. Otherwise, I will come up with the hall measurement in the next tutorial. Okay, so I'll make a slide on that. So how do we calculate the mobility, conductivity, and how can do that? Mobility, I can tell you directly here also. In why how do we calculate the mobility is, so you were in previously when I talked about the FETs. Were you there?
Yes, sir. Yes, sir.
Okay. In FETs, what we okay we in FETs we see IV characteristic, IV current voltage characteristics. Okay. So in current voltage characteristics, there are two type of characteristics. One is transfer characteristics, and one is output characteristic. Okay, in transfer characteristics, these are IDS. Okay, there was a current in between source and drain. Okay, so how this current so in between source and drain varies with the application of the gate voltage. Okay, so this is a three terminal device. I am just telling you, this is source, this is drain, and this is gate. Okay, so how the current flow IDS in between the source and drain is affected by the VGS. Okay, this is the VGS. The voltage source is always grounded actually. Okay, we ground it and we apply the potential at drain. So in between the source and drain, there in the current between source and drain is IDS. Okay, IDS versus VGS. This curve we find. Okay, so from this curve we can actually calculate the this mobility mu. Okay, so what we will do is, we whatever material you are saying, we will take that material, we will make the FETs, and we can find out, we can take the transfer curves of that, and we can calculate the mobility in that. There, like in these, but these mobilities are not the real mobilities. That these will be different. These are known as field effect mobilities. Okay, field effect mobilities, they are a bit different from the electron and hole mobilities. In different devices they will be different. Definitely in different devices they will be different. So LEDs they will be different, and FETs they will be different. In other devices, they will be different. They will depend on device to device, but we can just estimate the material properties through this. Okay, so any other question? So from
No,
this,
sir.
so through these, there are many methods. These are known as the electrical characterization actually. Okay, so what we were discussing about, okay, this one EK diagram. Is there any doubt in the seventh question? Anyone? Okay, so now let's move on the eighth one. The effective mass of an, okay, this is multiple correct answer. Okay, the effective mass of an electron inside a periodic crystal. Huh, inside a periodic crystal. Okay, there are some actually I don't know about the crystallography, but you might have heard about this, the cubic lattice, hexagonal pecs. There are some structures. Okay, so what happens is, in cubic lattice, so there are, these are the like atoms at the edge of the cube. So this is that the it when there is a atoms arranged in a lattice, so they they will form a cube. Okay, so because the distance from center of this atom to this atom, in this direction, in this direction, in this direction, inside this, in every direction it will form a cube. Okay, so that's why it is a cubic. So whichever whatever electron will go from through this lattice, so it will encounter the same, if it is going in x direction, in y direction, in z direction, in any direction, if it will go, so it will encounter same kind of the periodic potential. Okay, so this is, if it is encountering the same kind of potential, it is known as the isotropic. Okay, this is for the cubic lattice only. What if there are another monoclinic, triclinic, hexagonal, this kind of lattices? So let's say this is hexagonal kind of structures. So there will be this. So distance between these atoms and this atom, and this atom. Okay, okay, let me change the color. So distance between this atom, this atom and this atom is different. Okay, the electron moving in this lattice, in this direction and this direction, will have a different potential. So the, if it is moving in different potential and will have a, in ek diagram, this will have a different curvature in this direction, the conduction band structure, curvature of the conduction band, and the curvature of conduction band will be different in this direction. Okay, so the effective mass in this direction will be different, m star, let's say m star 1, and this m star 2. Okay, these will be different in both directions. Okay, so this is known as anisotropic. Anisotropic. Okay, so the effective mass will be different in different directions. That depends on the lattice. That depends on the material to material. So the effective mass is an anisotropic quantity. Okay, let us see who can be anisotropic. This is the first one. This was it. Captures all the quantum mechanical effects. Yes. So okay, quantum mechanical effects comes with this curvature. Okay, so in effective mass that we have seen, this captures the curvature of the conduction band. ठीक है, this curvature is the solution from the Schrodinger equation, and that Schrodinger equation accounts for all the these quantum mechanical effects. Okay, the boundary conditions in that, boundary conditions. You might have solved all these things. Actually, I am not that much aware about these things. But the boundary conditions, with the boundary conditions, when we solve the Schrodinger wave equation, so that captures this ek diagram is because of that only, and that captures all these effects. And and this m star is because of this curvature only. So this indirectly captures the quantum mechanical effects. Okay, so m star, this is, so because of this m star only, you can apply the classical model, classical mechanics, this that is like uh, physics laws. Force is equal to mass into acceleration. Just this one thing, this, the m star, just do the m star and you can do your calculations directly, just because this m star captures everything. So what does it mean is like, uh, when electron was moving in a free space, there is mass of the electron was like the constant. But whenever it moves in a space, there are so many interactions with the other atoms. Okay, So that is also captured as a dielectric constant also. Okay, so this captures, so ultimately this mass of the electron, that effective mass of the electron is capturing everything. Okay, so varies with the time. No, it cannot vary with the time, because there is, uh, what should I say, with time, we are not changing the lattice, right? We are not changing lattice, is the atom here and here, they will always be here. So we are, if the atom is moving this side, so with the time, if atom is moving, if the atoms are moving inside a lattice, then only we can say it, the effective mass is changing. Okay. Okay, if atoms are not moving, then we cannot say is same as that of the rest mass of the electron. No, that we have already discussed, because of the atoms, they this is because of the interaction with the atoms. No, this cannot be the same, may or may not be. Okay. Now, what should be the temperature in Kelvin for all the energy states below the Fermi energy level in the field? Okay, just uh, temperature. Okay, so Fermi Dirac distribution. Okay, so I might have written that thing. Let me check. Fermi Dirac 6, 5. Mm, yes. Okay. So, do you know about the Fermi Dirac distribution? Because this is more about the physics, not less. Actually, the statistics, not about the, uh, because of this Fermi Dirac distribution, we are just calculating the number of electrons or number of particles that are in the field state. So actually we are calculating the probability, because this Fermi Dirac distribution actually tells about the probability of the electron that can be at a state, that can be found in a particular state. Okay, so actually I sometimes I just forward, so that I wrote this in this one. So probability of finding an electron f of E, this energy at any energy level E, this is the probability. Okay, probability of finding an electron at energy E is given by the Fermi Dirac distribution, which is given by 1 divided by 1 plus exponential of E minus EF divided by KB into T. Okay, this Kb is the Boltzmann constant, and this is the relation that was given by this Fermi and Dirac scientists. Okay, so if you plot for what they are saying, the energy, okay, I will show you something. If E is greater than EF, okay, if E is greater than EF and E is greater than EF, this is a positive quantity, right? This is a positive quantity, and whatever, if, okay, uh, t goes to 0, this will go to infinity plus infinite. Okay, okay, ha, ha, okay, if E is greater than 0, okay, if E is greater than EF, E is greater than EF, what will happen is this exponent, and t, for t is equal to 0, t is equal to 0, this is the case that we are taking. E is greater than EF, E is greater than EF, this is the positive quantity, and T is equal to 0. So it will be exponential of plus infinity, plus infinite. So this will go to infinite. This whole term 1 by infinity, 1 by infinite is equal to 0. Okay. So whatever, for all the energies greater than the EF, the probability of finding an electron at T is equal to 0 is 0. Uh, did or did you get all? Did you all get this thing? Get this point? Like, if for T is equal to 0, for all the energies greater than EF, the probability of finding an electron is 0. Okay, so this is the energy E, that what we make in the Venn diagram. Okay, this is the energy E. Okay, this is the energy E. So this is, let's say, EF. Okay, okay, let me, okay, yeah. Huh. So this is the energy EF. So for all, so probability of finding any electron above this EF is 0. So whatever the conduction band over this, what, so this is the conduction band and this is the valency band. So valency, so probability of finding an electron above EF is 0, 0 at T is equal to 0. So that's what we say, that there are no electrons in the conduction band at T is equal to 0 Kelvin. Okay, you cannot find any electron in the conduction band. All the electrons will be filled in the, this is the electrons, okay, in the valency band only. Okay, so this is the case for the when EF is equal to, when E is greater than EF. So as I already told, that if uh, E is less than EF, what will happen? E is less than EF. So F of E, the probability of finding an electron at any state, which is 1 over 1 plus exponential of E minus EF divided by KB into T. So if E is less than EF, this term is negative. Okay, this term is negative, and KBT, T is equal to 0. This is minus infinity then. Okay, okay, exponential, it should come, huh, exponential of minus infinity is 0. Okay, e raised to power minus infinity is whatever. Okay, this is 0. Okay, so this is 0. So whatever so probability of finding an electron below the EF is 1. So if there are any states, next, uh, so this was the conduction band, this was the valency band, and this was the EF. Okay, so all the states below EF at T is equal to 0 are filled, are filled, because probability can be, probability of finding an electron PE, that can vary from 0 to 1. Okay, 0, 1 is the maximum probability, 0 is the, there you cannot find anything at that point. Okay, so 1 indicates that it is the short, you will find an electron at the energies levels below the EF. So if there are defects in the semiconductor, okay, this is the conduction band, this is the valence band. So if there are defects in the, in between this, so all the defects above EF will be empty. Okay, there won't be any electron. So all the defects below EF, defects are nothing but the energy levels. Okay, all the energy levels will be occupied. by the electrons. Okay, all the energy levels will be occupied by the electrons, whatever, whether they are defects or the valence band energy levels, whatever, the, below EF they will be filled. So this is the thing. So if we plot the graph in between, this is the E, this is 0 to 0, 1, 2, 3, 1. So EF, below EF, this is 1. Okay, below EF, okay, this is below EF. The probability of finding the electron, this is the probability, PE. Okay, probability of finding an electron. What is the probability of finding an electron below EF? It is 1. Okay, it is 1 below EF. Okay, so above EF it is 0. The so probability of finding an electron below EF, and below EF is 1 and above EF it is 0. This is 0. This is okay. So this is the probability of E versus probability of finding an electron graph. Okay, so this was the thing. So anything, so anyone has doubt in this thing, probability of finding an electron? Okay, I assume
No,
no one.
no,
Pooja?
no, no, sir. No, sir, no doubt.
Okay, okay, okay. So because this is the basic for to calculate the energies, like to calculate the number of say density of the charge carriers. So this is the basic of that, density of the charge carriers, or to find the density of the charge carriers. Okay, so now what is the probability of finding an electron? uh, I'm doing question number 10. Okay, till 10 I will ask later about after 10. So what is the probability of finding an electron at an energy E? uh, at energy E equals to the Fermi energy EF. So at EF, what is the at T is equal to 450 Kelvin. Okay, okay. The relation was F of E is equal to 1 over 1 plus E exponential of E minus EF by KT. Okay, so at 450, so KT at 450 you can calculate. We will see later. 450 degrees Celsius or Kelvin? 450 Kelvin. Okay, kVT we can calculate this. So E at E is equal to EF. Why I am not calculating? Because it is asking me at Fermi energy, what is the probability of finding an electron? Okay, at Fermi energy. So E is equal to EF. When both are E is equal to EF, EF minus EF is equal to 0. Okay, so this is 0. 0 divided by something is 0. Okay, so exponential of 0 is what? So F of E is equal to 1 over 1 plus e raised to power 0. So exponential of 0 is 1. Okay, so 1 over 1 plus 1 is equal to 1 by 2. The probability of finding an electron at Fermi level at 450 degrees Celsius, 450 Kelvin is 0.5. So actually there is nothing about the temperature, whatever be the temperature, whatever. So this finding, the probability of finding an electron is always 0.5 at EF. Okay, the electron can occupy or cannot occupy at the, if there will be any state at this, any energy state at this, so they can occupy or they may not occupy. So that is the 0.5. So my laptop is training. I do not have the charger now, so I think it is still 20%, no problem. So why the concentration of, okay, mm, okay. How many questions are there in the assignment actually?
It's
Hello?
12 questions altogether.
12 questions.
Yeah.
Okay.
We are ready to do 2 questions.
Okay. Let me check last two. Hmm. So, why the concentration of the electrons at the mid of the band gap of an intrinsic semiconductor is zero, though the probability of finding an electron over there is half? Yeah. Okay. Yeah, I just told you about the conduction band and valency band. Okay. So intrinsic semiconductor means there is no doping. That pure semiconductor. If there is a silicon, the band gap in between silicon is 1.12 electron volts. Okay. So this is the easy, and uh, the Fermi level is at the middle. This is the EF. Or do you know the definition of the Fermi level? So actually this is just an imaginary thing. So we just made this to understand the electronic devices, or to understand the charge carrier concentration in the conduction band or the valence band, the relative charge carrier concentration. Okay, so this there is nothing kind of, this is there is no real thing in the world such as the Fermi level, Fermi energy. So this is just an imaginary thing that we have introduced for our own, uh, our own, better. Okay. So this Fermi level. So Fermi level is nothing. That Fermi level is like finding uh, finding electron or hole, whatever you say. If there would be a state, there would be an energy state. The finding of the electron at any temperature is 1 by 2, 0.5. The probability of finding an electron at that level is 1 by 2. Or we can say the probability of finding the electron below that is 1, and above that energy level is 0 at 0 Kelvin. So this is the definition of the Fermi level. Nothing. Okay. So another thing, no energy states are allowed at the mid of the band gap, because there are no energy states. Yes, because in between conduction band and valency band, because the energy levels are already splitted. All the energy states are above the conduction band, band edge. This is the band edge, above the conduction band edge, and all the other energy states are below this valence band edge. So there are no energy states in between these two. Okay, so that's why you cannot find any electron at the Fermi level, despite there is a 0.5 uh, probability of 0.5 finding an electron at that level, but there are no electrons. Okay, there are no energy states. That's why we cannot find any electron in that state. If there would be any energy state, either by the defects that is it has given that it is intrinsic, so there are no deliberate defects in that semiconductor. So we create the defects. Defects is doping are defects, nothing. Just when we dope the semiconductor, we create the defects. Okay. So this is fine, correct. And the electrons does not have sufficient energy. No. Electrons have the sufficient energy with the phonons. Okay. At room temperature, it is asking the concentration of the they must be, though the probability of finding. So they have not mentioned any temperature actually. Why the concentration of electrons at the mid of the band gap of an intrinsic semiconductor is zero, though the probability of finding an electron. or there is half. So electrons does not have the sufficient energy. Electrons do have the sufficient energy at T greater than 0 Kelvin. Okay, so there is always a probability of finding an electron, but there are no mid gaps. Okay, because of there are no mid gaps, but there is sufficient energy. So no mid gaps, that's why we cannot find the this electron in that state. So A is correct, B is false because both are counter. Okay, so the density of states is 0 at the mid gap of the band gap. We haven't introduced, I think, that density of states thing. So because there are no, as I said, there are no states in between the conduction band and valency band. So the probability is still there, but uh, we cannot have this thing the electron in between. So the density of electrons density, the charge carrier density, that is the nothing but multiplication of the probability and density of states. That's it. Okay, that we will introduce in the next tutorial. So next time I will make slides actually, just because I couldn't do that because I had my presentation today, so I couldn't do that. I just saw this assignment also. So next time I will make presentations perfectly. So I will introduce some more concepts also along with the questions, and the density of states is 0 at this is the correct thing. So the electrons does not have sufficient momentum because there are no states. There cannot be electrons in the states. Whatever it is, they are saying the momentum is sufficient because it is already still going from the conduction band to the valency band at the room temperature. There in silicon only, there is a density of electrons. Finding electrons in the conduction band, the density is 10 raised to power 10. Okay, density of per centimeter cube. So this is indirect band, and still they are going. So they are changing the momentum also. That K. Okay, the indirect band gap semiconductor, and it is changing the momentum also, and that's why we can find the electrons in the conduction band in silicon, which is the density of that is 10 raised to power 10 centimeter per centimeter. So this is not the restriction, I hope. Okay, so this is a numerical problem, the last one. Okay, so assume the Fermi energy level is zero point 0.2 electron volt below conduction band energy. Determine the probability of the state being occupied by an electron at EC, conduction band energy. Okay, that we can do. KT is 0. Okay, 300 Kelvin. Okay, determine the probability. Okay, FE, that we will directly can see. Okay, EF. No. Okay. Probability. Yeah. Huh. Huh. Uh, hmm. Probability F of E. Just a minute. यार कौन आ रहा है? Someone came. Someone wanted to join. So he left. Huh. Huh. F of E is. अरे यार. Why? Huh. Okay. Okay. Huh. F of E is equal to 1 over 1 plus exponential of E minus EF by KT. Okay, ठीक है. हाँ, so
E minus EF. Mhm. So this I need to once think about it because uh, they are saying at the conduction band EC. Okay, Fermi level is just below 0.2 electron volts. Okay, this is they are asking what is the probability of finding an electron at EC. This is EC. At EC, uh, if the difference between the Fermi level and the conduction band is 0.2 electron volts. Okay, this is F of EC is equal to 1 over 1 plus exponential of this the difference between these two is 0.2. EC minus EF is 0.2 because this Fermi level is just below 0.2 electron volts. Okay, 0.2 electron volts of the conduction band. 0.2 divided by 0.026. Okay, when you will solve this one, so should I solve? Okay, I will solve that in my mobile. So can anyone solve this thing? Can anyone just solve it? Arey yaar, what happened?
Yeah, yeah. I've solved it.
Huh. You have solved it?
Yeah,
Huh.
yeah. The answer is like 4.5 into 10 power minus 4.
Okay, okay. This is in the so you did the same thing, right?
Yeah, yeah, I did the same.
Okay, okay. You got the concept, right?
Yeah, yeah, I got the concept. The same expression
Okay,
what
okay.
we've used. We've
Haha.
used the same expression and got the same result.
Yeah, okay, okay, fine. Because they have given all the values.
Yes.
Okay. So they have given all the values, and this is the and A is the answer in this thing. Okay. Ha. So okay. So can we have some interactive session a bit? Actually, I just wanted to know your backgrounds. So okay, just let me see. Huh. Okay. So uh, you can see me and you this screen. I'll let it be. So uh, can uh, can I ask one by one? Uh, I think Mohammed Farhan. Farhan, can you turn on your mic once? I think he is not there. Okay. So then, huh, Farhan.
नहीं बंद करिए वो
Huh,
बंद करिए
huh.
अरे कोई बंद करिए
Okay. Farhan.
यस
So,
सर
what is your background actually? Okay. Okay. Farhan is busy. Okay. So, huh.
क्या हुआ
Just okay. Likhita Sidhu. Okay.
सर
Likhita, what is your background actually, so that I can know next time I can prepare according to that only.
So background, do you mean by like my
Uh,
branch?
so what are you currently? What are you doing?
So currently I am pursuing my BTech in Jane to UK and I am in second year right now.
Okay, BTech. Okay, okay. Electronics, electrical, whatever. Which branch?
Electronics.
Huh?
I am from electronics.
Electronics. Okay. Which institute?
Jane to UK, sir.
JNTU. Okay, 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 fine. So electronics. So you might have been studying the basics of semiconductors, right?
Yes, sir.
In the second year, you are second year. First semester,
Yes, sir.
this course I think comes. Uh, so there are some books you can refer to, like Banerjee Streetman and Donald Neyman. They are really very good books. Okay, so for your if you really want to understand the basics of the devices or very basics of semiconductor physics, just refer these two books. These two books are more than sufficient. Okay.
Okay.
Uh-huh. So,
May you repeat the names of the books once again, sir?
uh, uh, one actually these are the writers. So Banerjee and Streetman's book. Just type a Streetman's book, so you will get it. Okay. So I forgot the name uh, of like maybe semiconductor physics or
Okay.
yeah. So one is the Banerjee and Streetman, and another one is Donald Neiman. This is for devices. Banerjee's treatment covers the physics part without mathematics that much. So if you don't want to introduce much mathematics, so you can you just want to grab the concepts like in depth knowledge you want to get. So you can refer to the Banerjee and treatment. Okay.
Okay, sir.
And another book is Donald Neiman.
Okay, sir.
Donald and Neiman. So these are two writers, Donald and Neamen. Just search on the Google, you will get. Okay,
Okay.
if you won't get, just uh, send me a mail if you have the mail ID. So I will share. Okay.
Okay.
So you have provided my mail ID or not? You all is
No.
there? Okay, so you can type in the chat box. I will share. Okay.
Okay, sir.
Yeah. And another so you can turn off your mic now. So Kritika, so Kritika is there? No. So Arabinda, Kritika, from which department are you, like electrical, electronic, or what is your background? Okay. EC, okay, okay, EC, which year? Okay, third year. You might so you have gone through this thing like semiconductor basics of semiconductor devices course. So you might have studied these books of. If you do not have, you don't worry. You didn't go through that. So now you can read about these books along with that. So it will be good. Okay. So for this course, when you watch the lectures, video lectures, parallelly go through that the books also. Okay, so it will definitely help you. So whatever these concepts I have introduced, the effective mass, this is really very good in the books. Okay, so they will help you, definitely they will help you. Okay, so Asmita and okay, all you are referral books. Okay, okay, I am writing the here. Okay, what Donald and Neiman. Another one is these are the two books. Okay, these are the two books. Just type on in the Google, you will get it. Definitely, you will get it. They are really highly studied. And one more book is that I won't suggest because that is too advanced for this course, which is and G SMG book. Okay, that is really very advanced. So for device people, that may help. Okay, so all others are Vijay. You can unmute yourself, Vijay Sai.
Yeah, yeah,
So, what is your background and what are you pursuing now?
yeah, yeah. Currently, I'm pursuing my PhD in VIT Vellore.
Okay, a PhD in VIT. Okay,
Yeah,
okay,
yeah.
okay. Yeah, okay, that's great. So, on which things are you working?
Semiconductor device modeling, actually.
Modeling you are working.
The modeling, right?
Okay, okay, okay. That's
I
great. That's
started my
great.
research like not at like
Okay,
recently.
which so which software are you using for the modeling?
Actually, I'm trying to use like the Centaurus TCAD.
Okay, TCAD. Okay, okay. Nice. Nice. That's great. That's great.
and
Okay.
also like the other tools like very
Okay.
low.
Okay. Okay. That's great. That's great. Nice. So you can write me if you need any other help for like materials. You can just write to me.
Yeah, sure. That's
Okay.
greatly appreciated. Right? Can I have your mail ID, please?
Oh, yeah, I will write. I will write my mail ID in this. Just you can mail me.
Thank you.
Yeah, sure. Anyone who has any doubts, you guys can mail me at any time. So whenever I'll see the mail, I'll definitely reply to you. Okay. So uh, now other people. Okay. Arabinda. Okay. Arabinda, if
Yes, sir.
so what is your background?
Sir, currently I pursue my BTech from
Okay.
Kolani Government Engineering College, second year electrical.
Okay, see, electrical. So you are also studying these semiconductor devices also. Electrical people also, I think they also have to study these things, right?
Yes, sir. Actually, I interested semiconductor, so I can join this course.
Okay, okay, okay. That's great. That's really great. So, okay. So if you also want to get depth, yeah, deep knowledge inside for the electronic devices, or maybe first you need to learn about the semiconductor physics. So, Banerjee and Streetman book you can refer to. Okay, that will be great.
Okay, sir.
Yeah, along with the course, whenever you see the lectures, whenever you watch the lectures, so along with that you can go through that book also. So that will be helpful for you,
Okay, sir.
definitely. Okay. Okay, that's great. So Asmita, I think you have already talked. I don't remember actually the names. Asmita. Okay. Dipali.
Yes, sir.
Hello. Huh. So what is your background and what you are doing currently?
Actually, I have studied diploma. Yes, yes, sir.
Okay, okay, continue, continue.
Okay, Asmita. Okay, Dipali. Just okay.
I have studied in diploma in electronics telecommunication. Now I am working as a technical assistant in KIT University, Odisha,
Okay,
Bhubaneswar.
okay, 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 okay. So you have studied all these things in your diploma, or
Not so detailed. We not so detailed, but now we are going so detailedly.
okay, 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 okay. That's great. So okay, so just go through the video lectures and assignments. That will be helpful. That will be they
Yes,
are
sir. Yes.
sufficient also. But if you just go, just you want to learn more and more, you can go through the books also.
Yes,
Okay.
sir. Sure.
Yeah. Sure. Okay. Asmita.
Yes, sir. Hello.
Huh.
Actually, I'm pursuing my PhD in KIT University.
Okay. KIT. Okay. Okay.
And actually, I'm doing the in this device only.
No, device only. So on which device are you focusing mainly?
Actually, now I'm doing on NC FinFET means
As a
education.
FinFETs.
Yeah.
Okay. 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 Actually, for all the devices, the basics is the same. So the like
Yeah.
conduction and
Initially,
so
yeah.
so that way this course
Mainly,
will be
I want to get clear on that band
okay.
diagram. That's why I've joined this course.
Okay, okay, okay. Actually, this is the like for any electronic device. If you know the Venn diagram, your half of the problem is solved.
Yeah, yeah, yeah. That is most very important part. Actually, actually, I'm in
Okay.
the verge to submit. Actually, in the mm, going
Your
to
thesis.
yeah, going to give
Okay,
my
okay, okay, okay. That's great.
thesis.
So,
Uh,
if you have any doubts, you can even write to the professor. Also, you can write to me also. Okay. So,
yeah.
whatever possible, I will tell about the Venn diagram, or if over a call also, whatever. Okay. So you can
Okay.
write to me. Huh.
Okay.
So
Thank you.
anyone who has any problem, doubts, or encountering any problem, so you can related to this this semiconductors, you can write to me or you can just call me directly. Okay. So I think mobile numbers are not shared, so you can directly calls on the Teams. Okay, you just write to me. I will. We can arrange a meeting also. Yeah. So now, Hira, Hira Jyoti.
Yes, sir.
Yeah. So what are you like doing currently?
Sir, currently I am pursuing my diploma,
Okay.
electrical engineering, second year.
Okay. Okay. Diploma. So are you in your diploma classes? Are you studying all these things like semiconductor devices and all?
Sir, yes, sir, it is started now.
Okay. Just like, huh. Okay. So now, okay, yeah. If you want to learn more deeply and if you have any doubts, you can just write to me. Okay. So, and
Yes, sir.
you are just you must have started the basics of this thing in the second year only, right? So you can go through the video lectures. I think video lectures will be sufficient. Okay. Uh,
Yes, sir.
Now, or if any doubt comes, so you can write to me or you can go through the books also. Books are like more than sufficient. Yeah. At this point in bachelor's, the books are sufficient actually. Okay. So if you have further you have any doubt, you can write. So now, Isha.
Yes, sir.
So
I'm pursuing BTech in marine engineering. I'm currently in first year.
okay, marine engineering. So marine
Yes, sir.
engineering. So actually, I am just curious. So about this course. So you want to learn about the electronic devices or like semiconductor physics? What do you want to learn in this course?
Semiconductor itself, because in our first year, just I have entered in second semester, so I
Okay.
found chapters related to semiconductor itself. And
Okay. That's nice. But I think in for the marine engineering, in the first year, all have the
yeah,
same sort of syllabus, right? Whatever is, if they are marine or if they are
yes, sir.
electrical, electronics, whatever, or and even mechanical people also learn these things, right?
Yes, sir.
Okay. This is the common one. Okay. Yeah, fine. So
Okay, sir.
I think for you, a very basics of the like video lectures will be sufficient. No need to go through the books because they will be very heavy for you. Okay.
All
So
right.
and if you want to go through the books, just read about the BZTs. I think BZTs they will teach in the first. So
Okay.
in these books, go through the uh, uh, BJT chapters, both the books. That will be sufficient for you.
Okay,
Okay.
sir.
Yeah. So
Thank you.
yeah, and now next is Kezia. Hello. Okay. I think no. And Sharvan. Okay. So I think they are not here. And if anybody left, so if you want you have any questions you can ask me or now we can leave also. I think it
Hello,
is.
sir.
Yes,
Sir,
Arvinda.
sir,
Yes.
please tell me, sir, please just tell lithography technique, sir, at least small amount.
uh
Actually, I don't know.
so okay. Next time I will prepare some slides that will be much better.
Okay, sir.
Uh, because lithography, you must know about the tools, what type of lithographies are used for, like, there are limits of the lithographies also. There are electron beam lithographies and there are optical lithographies. And direct lithography, indirect lithography, there are, okay, lithography is nothing but transferring a pattern. Okay, so, have you ever seen in like uh, in your childhood you must have used a stencil, which is there are like holes with A, B, C, these things, right? You
Yes, sir.
must have seen. So this is nothing but a transferring a pattern. So you just what you do is you just roll your pen with in the hole, so it will write A, B, and C is this kind of thing. So that is, the stencil is nothing but lithography mask. Okay, so this is the idea of transferring the pattern. Okay, so with the, when we go lower and lower limits, our pen has a limit. Okay, so it cannot write below certain. I want to leave. Yeah, sure, sure, Dipali, you can leave. And so our pen has a limit. So there is a, so this will have a limit. So it cannot write. It cannot draw a line below this dimension. Okay, whatever the dimension of the tip. Okay, so it cannot write. So we need to go for lower dimensions, right? So we need to go for different pen or different thing. So so different lithography techniques will do that job. So electron beam lithography goes in the nanometer. So then again comes a UV lithography, deep UV lithography. Then UV lithography can, we can write the pattern with the, I have done with till 5 micron, 2 micron, till 2 micron I myself have done. Okay, so with the my lab mates have done till 50 nanometers. So here we have the facility to do the lithography. So we can make the devices with the 50 nanometer feature size here. So when we go for the like commercialization for the industries have, we have these these instruments for the research purpose, to understand the material properties. So when we go in the industrial industries, so they have very better, very good equipments, or we can say the tools, because they need to sell the things in the market. That's why. Okay, so I will tell all about this in the, maybe in the next tutorial. Okay.
Okay, sir. Okay, sir.
Definitely. Yeah, sure. Any?
Sir, one question again, sir.
Yes.
Sir, please suggest us any book of material science.
Material science. Material science. I will check once, but I don't know about this, because in which year you are? So what are you doing these days?
Sir, I am in second year.
Okay, second year. Second year, there is no requirement of the BTech second year, right?
Yes, sir. BTech second year, but sir, interesting.
Actually, there is no that much requirement. You just go through these books, just understand the basics of the fundamentals of the semiconductor and the semiconductor physics, fundamentals of the devices. So in both these books you will get too much. Okay, so after that you can go to the materials later on. Huh.
Okay, sir.
Yeah. Anyone else? uh, are there any questions? Made up. Okay, my laptop is draining, so just a minute. So someone has. Okay, my laptop is. How much battery is 6% only. Okay, so someone are all different colored LEDs made up of different materials. Uh, there are n number of colored LEDs. How to, how it is, all this possible? Actually, the, okay, the display is made of red, blue, and green. Okay, are red, green, and blue. Okay, so these color, the combination of these colors can make any color in the world. Okay, RGB. So these are the basic colors. So with the combination of intensity of these colors, you can make any uh, color. So with a single pixel contains these three LEDs. they are of different material, of course, and may be different material, or maybe with the same material with different what say the ratio, like gallium arsenide or gallium nitride. The ratio will define that. Do you know the band gap tuning? Kritika, right? Kritika, do you know the band gap tuning? So with the ratio of these, like gallium arsenide, gallium ratio of the gallium and arsenide, we can tune the band gap. Gallium nitride, with the ratio we can tune the band gap. So with band gap engineering we can make the uh, uh, different colors of the LEDs. So they can be of the same, or they can be of the same material, or they can be of the different material. So in the next class also I can confirm whether in the market they are of the same material, or with the different material. But definitely they are with the red, green and blue LEDs. Okay. The single pixel contains these three LEDs. Yeah. Any other doubt? Hmm. Actually, my laptop is draining now, so can we leave now? Or if you have any doubt, you can just write to me, or next tutorial you can ask. Okay. And okay, just so Vijay, you did you record this lecture?
Yeah, I just recorded. I'll forward you the link of that, like maybe in that Google Drive. I'll share you with that in your mail ID.
Okay. I will download it and I will upload
Yeah,
in the
if
meeting.
the size limits me, it's fine. I can mail you directly. Otherwise, I'll just share you a link
Uh,
where you can just
yeah, share the link. Actually, it will definitely limit the size.
Yeah, yeah,
Definitely.
okay, sir.
Yeah.
Okay.
Okay. Okay. You all can leave now.
Thank you.
Yeah. Yeah. Thank you, sir. Thank you.